me introduce you. Our main presenter, James Wooten, who is also an FBAC member and the Planetarium Astronomer at the Houston Museum of Natural Science, an adjunct professor at University of Houston, and also an educator for Houston Independent School District. James instructs HISD fourth graders and the general public at the HMNS Burke Baker Planetarium, and also answers astronomy questions from the public on behalf of HMNS. I know he's out there to Georgia a lot answering those questions, and edits scripts for future planetarium shows to ensure that they are scientifically accurate. James has a Bachelor of Science in Physics and Planetary Science from MIT. That's a great university, and a Master's in Astronomy at Rice University. So I guess, James, without further ado, the floor is yours.
Okay, and we're going to talk about dark matter and dark energy. If you look at those names, those don't mean anything. That's that dark stuff. You have to remember to beware of placeholder names in science. We're still studying this to see what it really is. Anyone who positively identifies what that really is will win the Nobel Prize in Physics. Then we'll stop using those placeholder names and we'll start calling them what they really are. They're dark, by the way, because they don't interact with electromagnetic radiation. They don't emit it, they don't absorb it, they don't refract it. And so that's what the word dark means. There's matter that doesn't interact with electromagnetic radiation, and there's energy that doesn't do that either. And it's dark. And that's all we know. And therefore, we have to use these placeholder names that mean nothing until we can iron out what they really might be. Okay, how do we know that there's dark matter? There are several observations. If you go to the next slide, you'll see that normally we expect things to orbit more slowly when they're farther away from a gravitational source. We know that Neptune orbits much more slowly than Mercury, for example, around our sun. And that's how gravity works. It's an inverse R² force. However, when we plot the orbital speeds of stars around galaxies, not just ours, but pretty much any galaxy, we don't observe that. We observe that the stars farther away from the center orbit as fast as the stars closer to the center. In fact, faster than the stars in the very center. And that's confusing. If visible light and visible matter were the only things present, we should expect the mass to be concentrated in the very center of the galaxy. Therefore, stars farther away should experience less attraction and should orbit slower. But we don't observe that. There has to be other mass present to explain the motion we're observing. Again, it's dark, and we don't know what it is, so it's dark matter. It's dark and it has mass. It's dark matter, but it has to be there. Okay, next slide. We can observe galaxy clusters, and you can observe how many galaxies are present in each cluster. You can observe how much mass would be required to keep all those galaxies bound together. The galaxies we see don't have enough mass combined to bind them all together. Yet the clusters exist. The galaxies are not flying apart. Therefore, there has to be other mass present. There's matter. We can't see it. It's dark. It's dark matter. We have no idea what it is, but we know it has to be there because these clusters actually exist as clusters, yet the galaxies that we can see, their mass combined is not enough to hold them all in bound orbits. Therefore, we know that the extra matter is present. We have no what it is, idea what it is, so dark matter. Next slide. We can look at this cluster. Can you all see that some of the galaxies you have these little wisps like this? This is gravitational lensing. And once you observe gravitational lensing caused by light traveling from behind a very massive object. And by the way, if you want to know what gravitational lensing is, light travels straight through space, but massive objects bend space. Thus, around a massive object, space itself is heavily bent, and therefore light takes a curved path because it goes straight through space, which is here bent, and thus you can get gravitational lensing, where you can see galaxies that are behind the foreground cluster are distorted. We can determine how much mass has to be there to cause that much distortion. The galaxies we see aren't enough mass to do that to that degree. We know that there is other mass present. It's matter, it's dark, you can't see it, so we call it dark matter. Next slide. Then you have the cosmic microwave background. This is radiation emitted from the time that was the earliest time possible to emit radiation, very close to the Big Bang itself. And the color variation you're seeing there has to do with Earth's orbital motion. That's a uniform background. But we launched satellites to be able to measure very tiny anisotropies, which means that tiny variations in the temperature. The temperature, by the way, is about between 2 and 3 Kelvin. Yeah. Go to the next slide. This Wilkinson microwave anisotropy probe was able to detect fluctuations of plus or minus 200 microkelvin. That's 10 to the minus 6. And the size of these fluctuations reflect whether there was radiation or baryonic matter, and baryons, by the way, are protons and neutrons, that was resisting gravitational collapse. This gives us an idea of how many baryons should be present. And there's not enough to account for the mass needed. Therefore, we have to have dark matter. Okay, next slide. Now, dark matter can be hot, warm, or cold. What that refers to is how fast it was moving in the primordial universe. Really, how far it could travel before interacting with something or slowing down. Kind of equivalent things. Hot, dark matter would be matter that was able to travel very far before having slowed down. Cold matter didn't go as far. And that indicates how many structures could form. Because if you have dark matter that can travel a long way before interacting with anything else, then it won't form any structure smaller than that. But we're convinced that now the dark matter is cold, which means it couldn't travel very far without interacting, without forming structures, which means that in the universe, structures are built from the bottom up. So in other words, small galaxies combined form bigger ones and so on, and not from the top down like solar systems, for example. So we're thinking that dark matter was cold, which means it didn't travel far before clumping with other dark matter and other matter and forming structures. Next slide. Now, one rival idea. See, every time we come up with something we don't understand, there's always the possibility that we don't really understand physics. We have a mystery in physics. We have to consider the chance that maybe we just don't understand physics. Maybe there isn't any other magic material out there. What if our physics is almost right? And so this guy named Milgram said, what if instead of F equals ma, you had this other variation where that extra parameter would be 1 if the acceleration is greater than some nominal acceleration, but it would be equal to this ratio for very small accelerations. And he fit data to observe rotation curves, that is, the graph of the speed of the stars versus distance you saw earlier, and came up with that. So that's what this alternates. Maybe there's no dark matter. Maybe we just have to modify Isaac Newton's physics. But next slide. This is a cluster called the Bullet cluster. It's in Carina, which means we can't observe it here in Houston because it won't quite rise. It's not near Canopus. It's even further south than that. But these are galaxy clusters that are passing through each other. All the galaxies missed, but the hot gas did interact. And the hot gas is more massive than the stars are. Therefore, if the dark matter isn't really there, you might expect that the gravitational lensing would follow the actual mass present and not the stars. But it turns out that the visible stars, not the dust, which don't have the most mass we can see, are doing most of the gravitational lensing, which means there's extra dark matter associated with the galaxies themselves. So that's one of the reasons we're more confident that there is dark matter and that the modified Newtonian dynamics does not explain the universe as well. Next question, next slide. What are the leading candidates? Again, this is probably one of those deals where you choose the acronym first and then find some words that fit it. No, NASA does that quite a bit. But you have massive compact halo objects, or MACHOs, weakly interacting massive particles, or WIMPs. And those are two that we talked about first. But it turns out that, by the way, massive compact halo objects would be very dark things that are made of normal matter, things like black holes or large brown dwarfs, just things that wouldn't shine on their own in the halo of the galaxy. And the WIMPs would be massive particles that interact only with the gravitational force and the weak force, but not with the strong nuclear force or the electrical force. That's why they're weakly interacting massive particles. But it turns out that we were excited at first because the WIMPs were looking like the answer. And I know as nerds, you always want the WIMPs to beat the MACHOs. But it turns out that the next slide, the most exciting prospect would be these particles, such as axions. By the way, axions are particles that we have not found yet, but they're postulated to explain why the strong nuclear force does not break symmetry. Basically, laws of physics shouldn't change. Under CP symmetry, the laws of physics shouldn't change if you reverse the charge or if you turn the molecules around or the particles around. But the strong nuclear force should break that and does not. And to postulate why that didn't happen, they postulate axions. If those are real, those may explain dark matter, but we have not yet actually seen them. So again, we can't cross off dark matter, put axions. We have to keep in the vague, meaningless placeholder term because we're not sure what it actually is at this moment. We just know that it has to exist. And like I said earlier, whoever discovers what this is will win the Nobel Prize in Physics. And then we'll cross off the word dark matter and put in what it really is. Next slide. Let's talk about dark energy. Again, in another placeholder term, it means nothing because we don't know exactly what it might be. We have an idea. Next slide. This has to do with the ultimate density of the cosmos. Will it expand forever or will it collapse? And that depends on the density, how much mass there is per volume in the universe. Yeah. And see if someone mentioned primordial black holes. Those will be MACHOs as well. We're looking at tiny particles and not large scale objects in terms of dark matter. All right, next slide. The density is low, the universe will expand forever. If it's high, the universe will ultimately collapse in what's called the Big Crunch. And at present time, we observe the boundary condition. Next slide. We observe that the universe is flat right now. The boundary, close to being flat, not exactly, but close to. It's close to what's called the critical density, the boundary condition between the open and closed. Next slide. So if the universe were closed, you could travel in a straight line and end up back where you started. Of course, you would have to have a bigger budget and a lot more time than we have in our hands right now. Maybe when Captain Kirk invents warp drive, he can be able to do that. If he was in a closed universe, we don't think he is. Next. And so the flat the universe is one where Euclidean geometry still works. Triangles, angles add to 180, for example. And the open one would be a geometry like a saddle. But we think the universe we observe right now is close to being the flat universe. Next. The measurements of all luminous matter suggest that the actual density is only a few percent of the critical density. And factoring in dark matter raises it to only about 0.3 times critical density. Therefore, we need dark energy to explain the observed flat geometry at present. Next slide. We have things called standard candles. One of them will be a type 1 supernova. A type 2 supernova is the one where a massive red supergiant is too massive, and when it stops nuclear fusion, under gravity it falls in onto itself, and then the interior collapses into a neutron star. The outer layers land on that and bounce back and tear the star apart. That's type 2. Type 1 supernova occurs when you have a white dwarf associated with a massive red giant. And if the red giant swells to too big a size, mass can fall off the red giant onto the white dwarf. Thing is, though, just as you might have a table ready for a certain weight and will collapse if any more weight is put on it, white dwarfs are like that. White dwarfs are held up by electron degeneracy. Under quantum mechanics, you can't have two electrons in the same quantum state, which means that you can't have two electrons. The quantum states would be like, where is the electron? How much angular momentum does it have? How much angular momentum does it have due to being near the proton, and so on. There are 4 of them, and they can't be the same for any 2 electrons. When any further collapse would force a violation of that halts the collapse of the white dwarf. And that degeneracy pressure is what holds it up, because fusion is stopped in the white dwarf. Well, that pressure can hold up only about 1.44 solar masses. Therefore, when the mass falls off of the red supergiant onto the white dwarf, if that raises the white dwarf's mass to 1.44 solar masses, then it has to collapse. But it can't collapse due to quantum mechanics. Therefore, boom, it blows up. And therefore, type 1 supernovae have the same mass, 1.44 solar masses. And that means that they have the same intrinsic brightness. And that means their distance is the only thing determining how bright they look to us. Therefore, we can use these supernovae to see how fast the universe has been accelerating in the past. Now, in other words, the ones further away should be decelerating slower, or should be accelerating faster, and the acceleration in the ones nearby should be slower, because in theory, things that expand slow down when they expand. Think of blowing up a balloon, for example. You blow it up, it expands, then it slows down. Well, we actually graphed that. Next slide. And we notice that the redshift of the more distant type 1 supernovae is lower. It falls off of the pattern, whereas the redshift of the ones closer by holds to that line. That means that they were receding slower. In other words, the universe was accelerating slower in the past than now. The expansion of the universe is accelerating. So you had the Big Bang, which began the universe's expansion, and that expansion is accelerating. We expected it to be slowing down. We expected that the mutual attraction of all the massive objects created in the universe would ultimately overcome the expansion and slow it down, but the opposite is happening. What causes the universe's expansion to accelerate? We don't know. So they've given that a very content-free placeholder name, dark energy. Whatever it is making the universe's acceleration expand, well, we can't see it. It doesn't interact with the radiation in any way, so it's dark. And there's some energy that somehow overcomes the gravitational attraction of all the massive objects in the universe, so it's dark energy, which says nothing about it, but that's all we know. Next slide. And so dark energy is our placeholder term again for the unknown force that makes the expansion of the universe accelerate, and the repulsive effect increases as the universe expands. So there's more dark energy over time, causing the universe to expand faster and faster and faster. Next slide. Well, one idea for what it might be, well, one way to describe it would be the cosmological constant. When Einstein first proposed general relativity, people held to what they call a steady state view of the universe. But general relativity predicts that all the mass in the universe should eventually attract, and thus collapse the universe, which is not what they were observing. Therefore, Einstein added a constant into his equation that he called lambda. And yes, I looked up why he picked lambda. I couldn't find why he picked lambda to represent it, but that was his constant. And the universe turned out to be expanding. Einstein removed it, causing it to move that constant, calling it the biggest blunder of his career. But, next slide. Now it seems like that constant will help explain the accelerating universe. Doesn't tell us what the dark energy is, but that constant will represent dark energy, which will explain why the universe's expansion is accelerating and not slowing down. Next slide. And so, given what we know now, the age of the universe works out to be about 13.8. It was 13.7 when I studied this, but now 13.8 is a better age of the universe. And we do have the accelerating universe. It's close to flat right now, but the universe is accelerating as we speak. Next, the expansion is accelerating. And so rough timeline, you had the Big Bang, 13.8 billion years ago, quasars, 13 billion years ago, and then 10 billion years ago, we had the first stars in our galaxy form. Next. So what is the universe made of? This graph shows that at the beginning of the universe's history, there wasn't any dark energy. So dark energy is something that builds up over time, mostly dark matter. But now it's mostly dark energy. And we have an updated today pie chart on the next slide. What is the universe made of? Next slide. We're thinking of 68.3% dark energy, 26.8% dark matter, 4.9% ordinary matter. That's things made of protons, neutrons, and electrons. All that ordinary matter is 40.9% of the universe. That means that we don't know really what 95.1% of the universe is. And that is why scientists still have jobs. That's why we can't just go home. We have to figure out what 95.1% of the universe really is. Our goal is to remove the meaningless placeholder term dark matter and dark energy and put actual words in that name what those really are. All we know right now is that there must be more matter than we can actually see to explain why stars don't go slower when they're farther from the center of the galaxy, to explain how certain galaxy clusters are still there when their visible mass isn't enough to hold them together, to explain why we see that much gravitational lensing more than the visible mass should cause, and so on. And we know there must be something that's causing the universe's expansion to accelerate. We think that Einstein's cosmological constant represents it mathematically, but what is it? We're still not sure. Therefore, we still have jobs to do. And by the way, our last slide, so we should rename the Big Bang model. Next slide. Because, as you may be aware, the term Big Bang was coined by Fred Hoyle, who did not accept the theory. It was a dismissive term to discredit a theory he did not accept. but now we're confident in it that that's the real origin of the universe. But there was never a big bang. No, there was no explosion. It's just the universe was hot and dense and all compact and then expanded. The better term for that we can't get lay people to use because it has a Greek letter in it and just acronyms, and will never replace Big Bang in the popular consciousness. But really, it's the lambda CDM model, where lambda is the cosmological constant representing dark energy, and CDM is cold dark matter. Because those two things combine to make up 95.1% of the known universe. Which really means that 95.1% of the universe is unknown. All we know is 4.9%. And with that, we'll pause and ask for any questions you may have.
Is there any ordinary energy? You had dark matter and ordinary matter, and you had dark energy. What about ordinary energy? Is there such a thing?
Well, I think that everything else that's not dark matter and dark energy goes into 4.9%. So in other words, the dark matter and the dark energy is 95.1% of everything the universe is. And we don't know what it really is. And everything we can explain goes into 4.9%.
Gotcha.
I had heard that there are two conflicting things on the Hubble constant, one which is done by the supernovas and one which is done by the observation of the cosmic microwave background.
Yes. Yeah, there is a disagreement on that. However, that doesn't affect whether dark matter exists or dark energy exists.
Right.
Yes. So again, there's so much in science, and I try to communicate this to the public and to the students who come. Scientists have jobs because we don't know.
Yeah. I know that the James Webb Telescope has just, started really turning things a little bit, topsy-turvy on some of the things.
Yeah, James Webb has seen galaxies that come from a time before we thought galaxies could form.
Yeah.
That their distance indicates that they formed so long ago before we thought galaxies would be able to form.
Yeah.
We have to rethink some things.
Hmm.
Another mind-bending part about this whole cosmology is that time can't go less than zero, just like you can't go north of the North Pole.
Yeah.
Which means t equals 0 is a singularity, and that means that 0 is not in the domain of that function. That means that time equals 0 is not in the universe. And neither is any time less than that, which means there's no before the universe or before the Big Bang. It's a meaningless question. Yes.
Can't have time without, events passing. If you can't see events.
Yes. Exactly.
This is a really good one. I love this subject. This is really good.
So one thing I've wondered about is why these galaxy curves, these rotation curves, are almost all of them are flat. And it seems to me, why wouldn't some galaxies have more dark matter than other galaxies? And so you would see a variety of curves, but they're all flat.
Yes.
And I think that's really weird.
The Milky Way is wavier, but yes, the stars seem to orbit at the same speed. Once you get past the very center, the stars orbit at the same speed. And hopefully once we find out what dark energy really is, we can explain that.
Yeah, so I just does any theory explain why all the galaxies seem to have enough dark matter to give a flat curve and not one that's tilted one way or the other? That just seems really bizarre to me.
Yeah, I have not found any such theory yet. I'm thinking that hopefully once we can positively identify dark matter, as we can cross off that meaningless term, put that in there, then we can explain why whatever that is has that effect.
And the other thing too is, how far out can you probe the galaxy rotation curve? In other words, we've got dwarf galaxies that are way beyond, and presumably they're in orbit around the Milky Way.
Yeah.
Are they still indicating kind of a flat curve, or is anybody looked at that?
Every galaxy, yeah. no galaxy that we've looked at shows we expect based on the visible mass, which is that the more distant stars should orbit slower. I haven't seen a single galaxy rotation curve like that.
Okay. Here, the final question is does this violate conservation of energy? I mean, we have more and more, the bigger space gets, the more dark energy we have. So where's it coming from? And does that violate conservation of energy?
Yeah, one idea is that there's a vacuum energy that exists when particles annihilate themselves, and that might be representing that, but that's still, again, we don't know. And that's why I know a young lady requested this to hoping was saying what this is. Hopefully I was able to explain shed some light on what we do know about it, and it's not much.
Yeah. But it sounds like this would violate conservation of energy, which is a pretty fundamental principle.
Yeah. Although there's also negative energy in the universe somewhere, but I know it's one physics problem set at MIT. We calculated the total energy of the universe and it was zero in some else.
Yeah, but if the universe keeps expanding and there's more and more negative energy,
yeah,
that seems like it's not going to stay zero.
Yeah. So
I don't know.
Right now, yeah.
Well, one thing to consider is, this is Todd. So let's just go back to what James was talking about, is that we have given names to these terms. We don't know what they are. So we call something dark matter, we call something dark energy. This dark energy concept could be something totally different from what we understand energy to be. And if this is the case, it may not result in any degree of violation of conservation of energy, because it may not really be energy. So we just have to, keep looking and figuring out and stuff like that. And James, one question that I wanted to ask you. Again, we have the concept of, well, maybe dark energy is a fundamental property of space. And as expansion occurs, that's how we generate more dark energy. Do we have any, are you aware of any experiments that have been contemplated to actually determine, say, what dark matter and dark energy might be?
In my research for this, I did not come across any, although I'd imagine there must be some.
Okay.
I had heard, though, that some people have been calling dark energy constituents axions, hypothetical particles.
Yeah, I mentioned the axion particles, which are particles postulated but not yet found.
Yeah.
Displaying why the strong force does not violate symmetry, and when really it should.
James, they have set up 2 experiments at CERN looking for axions, and neither one of them were successful.
Yeah. No.
That's the thing. I wonder if dark energy came first and then the galaxies formed around it.
Yeah, would be dark matter came first. The galaxies wouldn't form around dark energy. They form around dark matter.
Yeah.
Well, I mean dark matter. I'm sorry.
Right. Yes, and that's possible that it came first, and that the clumping of dark matter is what allowed galaxies to form.
The other thing is interesting is that dark matter is an attractive force, and dark energy is a repulsive force.
Yes.
And never the twain shall meet.
Yes. Dark matter has gravity, which was attractive, and dark energy is repulsive.
That's right. And we haven't yet run across the dark equivalent of magnetism.
Yeah.
We don't think we have anyway.
Although, so with knowing that there's 2 kinds of the electromagnetic force has 2 kinds of forces. So we model it mathematically as positive and negative. But as far as you know, gravity is only there's only one sign ever. And
that's right. That's negative. The other thing is that we humans are entirely made of electromagnetic stuff, and all of our senses are electromagnetic. We have no senses that would detect on their own dark energy or dark matter, for that matter. We apparently that never developed on Earth. No, none of the fossils that we've run across have strange things that we don't know what that could possibly be an antenna for. We've got eyes that are antennas for a certain narrow band of light, E&M energy. We've got skin that feels a very narrow band of infrared energy. We can detect ultraviolet energy when it burns us. We can set up machines that use the other portions of the electromagnetic band, but everything we do is E&M, is electromagnetic energy based. And it may be that we're going to have to figure out some other antenna or antenna-like device in order to do this. We're just not.
That's
we're
the
just not
challenge of
using the
having
right
something
instruments.
be this dark. And again, dark means it does not interact with
Yeah,
electromagnetic
exactly.
radiation. Not that it doesn't emit it, doesn't absorb it, doesn't
Yeah, it doesn't reflect it, doesn't
scatter
absorb
it.
it, doesn't
Yeah.
transmit it.
Yes.
Yeah, so I think we're sort of waiting for some
Yeah.
bright individual to come up with an idea
And
about
that's
how.
why the tiny particles
Yeah,
were the better chance. But again, we haven't found any of them. So we're still stuck with dark matter, the meaningless placeholder label for stuff we
yeah.
don't know what it is.
This this whole topic deeply affects thermodynamics, and there's a lot of work being done on the thermodynamics of the idea of this, and non-local forces, what entanglement means in terms of thermodynamic energy and results, and what this means for second law of thermodynamics. It's a hot topic, and it's got a lot of workers working on it.
I don't know. I think when my cats are staring at the wall, they're detecting something, so.
Remember that most animals have better smell and hearing than we have.
Yeah, that's true.
So that wouldn't be dark matter though. It would be something else, something.
Yeah.
It makes me wonder whether dark energy is like Schrodinger's energy, and that once we observe it, it's not
It'll
there.
go away.
Yeah.
That we
Well,
can
I
only
suspect when we
speculate
finally,
about
when
these
some
things.
smart guy finally figures it out, everybody will go, of course.
Yes.
You know,
In fact, the next
I'll
year
be-
there'll be a homework in the problems at MIT.
yeah, yeah.
Hey, James, I have a question.
Yes.
I remember when dark matter was a much newer topic, let's say 20 years ago, whatever it was. They talked about not so much stuff that's out there, but they were talking about that we have to adjust the Newtonian gravity
Yes.
theory.
Yeah, that's what I mentioned, the modified Newtonian dynamics, but they found that cluster I showed you where the gravitational lensing effect is more pronounced around the actual visible galaxies, not where most of the mass is, where the dust is interacting, which means that dark matter around those galaxies is causing most of the gravitational lensing. That's the better explanation for that, as opposed to the modified Newtonian dynamics. That's one reason why most physicists and astronomers think there is dark matter, and they don't think that that modified Newtonian dynamics, as it stands now, is a better explanation.
There is a galaxy that we've found that doesn't seem to have any dark matter associated with it. Yeah. And a question before the House is, how come?
Yeah. Again, once we explain what dark matter really is, then we can investigate which galaxies have it and which ones don't. And the question that that was asked earlier about, why all the curves the same? Again, I think we have to know what it really is to really get a handle on that.
Vera Rubin's article on the radial velocity curves for galaxies, she followed nebula, she followed clouds,
Yes.
you know. She didn't follow individual stars. Yeah, if you remember. Yeah. She essentially did what Fritz Zwicky should have done.
Well, I've also heard about tired light.
Yeah.
Yeah, but again, the simple explanation that seems to explain everything better is that speed of light really is the speed of light in the vacuum really is a constant,
Yeah.
Yeah.
and it doesn't get tired.
Yeah.
Yeah. One of the questions that is bouncing around is how does light cross those huge voids in the cosmic net? Because those voids are big enough and empty enough to where they should, if light is going to get tired, or if a magnetic electron is going to get tired, it should do it in those big voids. But
Well,
apparently it's not happening.
A photon is a set of oscillating magnetic and electromagnetic fields, and thus the intensity falls off with distance. But I'm not sure if you have anything that would make those electromagnetic fields weaken over time, then that would do it. But that's what a photon is. A photon is basically particles are best understood as spots where fields become excited. And so really have interacting fields in the universe as opposed to particles. And the electromagnetic field, you have an electric field oscillating one way and a magnetic field oscillating in the perpendicular direction. And that's what a photon really is. And it doesn't need a medium to pass through to stay that way. So a void might just be nothing to pass through.
Yeah. There's a book by Katie Mack called The End of Everything, Astrophysically Speaking, which touches on these topics. It's a really good book. I recommend it.
Repeat the title again.
The End of Everything, Astrophysically Speaking.
Oh.
It's
Katie
good.
Mack's a cosmologist.
It is good.
Yeah.
The end of the world as we know it, and we feel fine.
The end of everything. That already happened on November 5th.
Yes. Any other questions? If there are no other questions, I will turn the meeting to Jeff Lipp.
Thank you, James. We always enjoy your talks. They're always very informative and of topics of interest to the club. So, and we also appreciate the advice you give us. I know observing or when we're out at the George volunteering, and all the help that we get from you as well when we're out there trying to explain things to the public, and you help us explain it better. Thank you very much.